This lecture deals with microstrip antennas. In this topic, you will be learning about the salient features of microstrip antennas. What is a rectangular microstrip patch antenna? Then what are the different feed methods used for microstrip patch antennas? And the characteristics that affect microstrip patch antenna. So to start with, what is a microstrip patch antenna? So basically a microstrip patch antenna is a very low profile, low gain, narrow bandwidth antenna. So it will consist of a ground plane. On ground plane, on top of it, it is filled with a dielectric substrate, and on top of the dielectric substrate you have a conducting material which we call as the patch, which is placed on top of it. Usually this patch will consist of a thin conducting sheet. It will be about 1 to 1 by 2 lambda naught length mounted on the substrate. So usually it will be radiating at the two slits at the right and the left hand of the patch. So even though if the length of this patch is only so much, some of the radiations will be coming outward of the conducting material. So those are known as fringing fields. And the slot is a narrow gap between the patch and the ground plane. And here a hole is there for coaxial line, and usually it will be fed at this point. Usually the patch to ground plane spacing will be equal to thickness T of the substrate and is typically of lambda naught by 100. Usually patch antennas are popular in the mobile phone market. So this is basic how a patch antenna looks like. So this is very basic a patch antenna. Also patch antennas arrays are formed in order to increase the bandwidth and directivity. It's another example where there is an array of patch antenna array. So what are the salient features of microstrip antennas? So from the diagram you can make out that a patch antenna basically as a metal patch suspended over the ground plane. Usually this assembly will be mounted on the plastic radome. Radome means it's like a plastic container which will protect the structure from damage. Usually this patch antennas will be simple to fabricate and it is easy to customize also. Usually some lithographic patterning is used to fabricate this printed circuit boards onto the dielectric substrate. Another feature, so from this you can make out this is the ground plane. So on top of it you have the dielectric and on top of it you have the patch. So a microstrip patch antenna will consist of a radiating patch on one side of a dielectric substrate with a ground plane on the other side. The simplest patch antenna will use a half wavelength long patch with a larger ground plane to give better performance, but at the cost of larger antenna size. So here the vector potential and thus the electric field will follow the current. So usually this kind of antennas will provide a linearly polarized wave. Usually it is a narrow band and a wide beam antenna, and it is fabricated by etching the antenna element into an insulating dielectric substrate with a continuous layer. One of the key drawback of patch antenna is their narrow bandwidth. That is, if you want to achieve a wider bandwidth, a relative thick substrate is used. Usually this substrate will support tightly bound surface wave modes which represent a loss mechanism in the antenna. So the loss due to surface wave modes will increase with the substrate thickness. So it is desirable to develop microstrip antennas which enjoy wide bandwidth yet do not suffer any losses. Now this microstrip patch antenna was developed by a scientist named Deschamps in 1953, but initially it was not so popular. But as the technologies improved and with the development of PCBs and microwave techniques, it became more practical antennas and it became much popular. And also microstrip patch antennas are often used where thickness and conformability to the surface of mount or platform are the key requirements. The primary limitation of this type of antenna is its bandwidth. Its bandwidth is very less, which is almost around 5%. And this bandwidth can be increased by adding one more substrate. Usually with that you can increase the bandwidth up to 35%. Now there are different types of patch antennas like square, circular or triangular or elliptical shape. It can be of any other continuous shape usually. The two most common geometries used is rectangular and circular is the most popular used. The square patches can usually generate pencil beam and rectangular patches are used for a fan beam. And also the size of the microstrip antenna is inversely proportional to its frequency. That is, if the frequency is lower, then the microstrip patch will be of very small size. If it is at X band, then the size will be of the order of 1 centimeter, which is easy to realize on soft board technology. Now another feature is usually microstrip antenna will employ a metallic patch which will be positioned on top surface of a dielectric substrate. The dielectric substrate has the bottom surface coated with a suitable metal to form a ground plane. So this ground plane will not be conducting, only the upper antenna patch conductor only will be conducting, but the ground plane will not conduct. And usually a hole will be formed onto the ground plane and through the dielectric to allow to the bottom surface of the patch. Then the last function is usually this microstrip antennas will be constructed on a thin dielectric sheet using the material. Usually a common board Teflon fiberglass will allow the microstrip antenna to be curved to conform to the shape of the mounting surface. And usually the conducting material used is copper or gold. Usually the radiating patch and the feed lines will be photo etched onto the dielectric substrate. So these are the different features of the microstrip antenna. Now what are the advantages of microstrip antennas? Usually the main advantage of microstrip antenna is it is lightweight and smaller size and it is of lesser volume. You can see from the size itself it is of very less weight. And they are very low profile and it can be molded to any desired shape and ends can be attached to any hose surface. And also in this case the fabrication process is very easy and cost is also very low. And also they can support both linear and circular polarization and are capable of dual and triple frequency operations. So different frequencies you can obtain and also you can obtain different types of polarizations. And with it is easy to form large arrays. As I've shown in the picture before, you can form large arrays of either 4 or 8 or 16 antennas together as an array with half wavelength or lesser spacing. So these are the advantages. But what are the limitations? First limitation is its low bandwidth. That is, as I've told you, it supports maximum 1 to 5%. And also it has only very low gain with low power handling capacity. Also they suffer from the effect of radiation from feeds and junction. Wherever we are feeding also there are possibilities of radiation and also from the junctions. And this provides very poor end-fire radiators. So usually when you consider the different types of antennas, they are very poor end-fire radiators. And also it has very, the surface wave excitation in these antennas is also an added limitation. So these are the basic limitations of antenna, and this can be addressed. Above limitations can be addressed by either using thick substrate or cutting slots in the metallic patch. So next topic is rectangular microstrip antennas. So rectangular microstrip antenna means the patch whatever, so it's a basically it has a ground plane, then you have a dielectric substrate, on top of it you have the patch placed on top of it. So here from the name itself you can make out the patch shape is rectangular. And here the length L is a length which is universally taken to mean the long dimension, and this causes resonance at its half wavelength frequency. W is the width and is referred to as radiations can occur at the ends of the W dimension is far less and is referred to as cross polarization. So you can see in this here fields are more on voltage is more on this side and current will be maximum at the center, and also even though the conductor is only so much size, you can see extra fields coming out of at the ends. Those fields we call it as fringing fields. So because of the half wave nature, the fields under the L edges are of opposite polarity, and the field lines curve out and finally propagate out in direction normal to the substrate. They are now in the same direction. And usually, as I've told you, length L and so for effective radiation, the structure needs to be half wavelength resonator with a thick dielectric material of low dielectric constant under the patch, but the height needs to be a fraction of the wavelength. So now if you consider a microstrip line, usually the frequency of operation of the patch is determined by the length L and the sender frequency will be usually given by the formula. The sender frequency is given by the formula Fc is equal to C by 2L into root of epsilon r, which will be equal to 1 by 2L root of epsilon naught epsilon r into mu naught, where C is the velocity, epsilon naught and mu naught are the permittivity and permeability of free space respectively, and epsilon r will be the permittivity of the dielectric substrate. Now for an example, if you consider a patch antenna with the dimension L is equal to 1.56 and W is equal to 1.25 centimeter is mounted on the dielectric substrate with epsilon r is equal to 2.2 and H is equal to 0.795 mm. Then the critical frequency will be equal to 4.37 gigahertz. So from this above equation you can see that the microstrip antenna should have a length equal to 1/2 of a wavelength within the dielectric medium. So next equation that you should remember is the frequency is also dependent on width W along with the length L, and the equation is given as C by 2 into root of epsilon r effective whole of n divided by L plus 2 delta L whole square plus m divided by W plus 2W 2 delta W whole square whole raised to half, where epsilon r effective is given by the formula 4 epsilon RA epsilon r divided by root of epsilon RE plus root of epsilon r. Here delta L and delta W are the incremental length and width which account for the fringing of field at the respective edges, and the other notation is general ones. Then in this the width W will control the input impedance, that is larger widths will increase the bandwidth also. So for a square patch fed in a manner above, the input impedance will be of the order of 300 ohms, and by increasing the width the impedance can be reduced. And if you want to decrease the input impedance, then you need more area, and this will again be controlled by the radiation, and the normalized radiation pattern is given by these formulas that is in terms of sine and cosine, for both for E theta and E phi. These are the equations. Here E theta and E phi are the theta and phi components of the electric field intensity E, and theta and phi are the elevation and the azimuth angles of radiation pattern, and K is given by its wave number and given by 2 pi by lambda, and the net magnetic field at any point will be a function of theta and phi is given by root of E theta square plus E phi square. So this is basically how the radiation pattern of the antenna will be, and it is very wide beam width. It can achieve very wide beam width. That is the advantage of having microstrip patch antenna. Now next topic is the feed methods. So you have different types of feed methods. That is, how do you feed the microstrip patch antenna? So these can be classified in a variety of ways. That is either contacting or non-contacting. So in this you have, in the contacting method, the RF power will be fed directly to the radiating patch using a connecting element such as microstrip line or a coaxial line. And in the case of non-contacting scheme, in that electromagnetic coupling is done to transfer the power between the feed line and the radiating patch. So some of the popular methods that has been used is feed techniques include microstrip line, then coaxial probe, aperture coupling, and proximity coupling. So first two cases will fall under contacting schemes, and the other two will fall under non-contacting schemes. Now considering the diagram, so sender feed means it is the one wherein the microstrip line is in the center of the patch, and offset feed is the one wherein it is not in the center of the patch. Next is inset feed. When an antenna is fed in the center of the width or at the end, the current will be low at the ends of the half wave patch, and it increases in magnitude towards the center along with dimensional. So the thing is that this can yield a high input impedance. The input impedance can be reduced if the patch is fed closer to the center. So this is illustrated in using inset feed method, wherein the transmission line extends by a distance r from the end. So in this case, the input impedance is given as Zn of r is equal to cos square into pi r divided by L into Zn of 0, where Zn of 0 is the input impedance if the patch is fed at the end. And by inset feeding, the input impedance can be increased. Now next is quarter wave line feed. So in this case, it can be matched to a transmission line of characteristic impedance Z0 by using a quarter wave session, that is lambda by 4 session can be used of characteristic impedance ZL. So if the impedance of the antenna is given as ZA, then the input impedance viewed from the beginning of the quarter wave session will become equal to ZL square by ZA. So this input impedance Zin can be altered by selecting suitable selection of ZL, so that Zin will be equal to Z0 and the antenna will be perfectly matched. So the parameter Z1, ZL can be altered by changing the width of the quarter wave strip line. The other methods are coaxial feed. So in coaxial feed, this is a very popular method used. So in this case, you have the inner conductor of the coaxial connector. It extends through the dielectric and is soldered to the radiating patch, while the outer conductor is connected to the ground plane. The position of feed can be altered to control the input impedance. So the main advantage of this method is that the feed can be placed at any desired location inside the patch in order to match with its input impedance. and it is easy to fabricate and has low spurious radiation. Major disadvantage is that the ground plane. You have the ground plane here. This will provide a narrow bandwidth and it is difficult to model since a hole has to be drilled in the substrate and the connector will protrude outside the ground plane. And also for thicker substrates, this will provide, what happens is the input impedance will become more inductive and this will create matching problem. So coaxial feed will introduce an inductance into the feed. So this has to be taken, need to be taken into account if the height h is larger. And this probe also may introduce radiations in undesirable directions. So these are the disadvantages of this method. Now next one is aperture coupled feed. So this is also called as electromagnetic coupling scheme. So in this scheme there are two dielectric substrates are used such that the feed line is sandwiched between the two and the radiating patch will be on top of the upper substrate. And this feed circuitry will be shielded from the antenna with the help of a hole or a slot or a aperture, and this to transmit energy to the antenna. And this amount of coupling between the feed and the patch, it is determined by the shape, size and location of the aperture. In this, the advantage is that spurious radiations are reduced much, and also it will provide high bandwidth due to overall increase in the thickness of the microstrip antenna. And matching can be achieved in this case by controlling the length of the feed line and width to line ratio of the patch. Only difficulty in this case is the difficulty is fabrication will be slightly difficult because there are two substrates and you need to properly align it. And also the overall thickness of the antenna also will increase in this case. Now next is proximity coupled feed. Now in this case, if the insert feed is stopped just before the patch or the probe feed is trimmed such that it does not extend towards the patch antenna, then it becomes proximity coupled or the indirect feed. So this is how it looks like. So the advantage of this is it adds an extra degree of freedom to the design, but the gap will introduce a capacitance and it will cancel out with the inductance added by the probe feed. So these are the different characteristics, feed mechanisms you have. So next topic. So this is the comparison of different feed methods. So in case of spurious feed radiation, it's more in case of microstrip line and coaxial feed, but it is less in aperture coupled feed, but minimum in case of proximity coupled feed. And reliability is much better in proximity coupled feed. Fabrication is easy in case of microstrip line, but others all it requires alignment, so it is little more difficult. Impedance matching is almost same for all the ones, but bandwidth is more in case of proximity coupled feed. Now considering the characteristics of microstrip antennas. So here in figure it is shown two radiation patterns, that is in phi equal to 0 and phi equal to 90 degree, that is in azimuth and in elevation line. And another radiation pattern is shown for linearly polarized patch antenna. So this figure shows a cross section in the horizontal or the azimuthal plane. So here the scale is logarithmic and the power is radiated at 180 degree is about 15 dB less than the power in the center of the beam at 90 degree. The beam width is about 65 degree and the gain is about 9 dBi. And an infinitely large ground plane will prevent any back radiation, but actually the real antenna will have a fairly small ground plane. And also the power in the backward direction is about 20 dB down from that in the main beam. Usually when you consider microstrip antennas, so the patch is the conductor, so the voltage and current will be usually out of phase. So voltage will be maximum at the end of the patch and minimum at its midpoint, and the field underneath the patch will be like of different fields as shown in the figure above, and the fringing field near the surface of the patch will be in the y direction. It will be in the y direction. Now the next parameter is beam width. So usually all the microstrip patch antennas have very high beam width both in azimuth plane and in the elevation plane, as you can see from the radiation pattern diagram. Next parameter is directivity. So directivity for TM10 mode is given by this equation, where D is equal to 2h square E naught square W dash square K naught square divided by PR pi eta naught. W dash is by considering the fringing fields, we will consider it as width plus height, and eta naught is equal to 120 pi, and K naught is the wave number, and E naught is the magnitude of the set directed electric field intensity inside the cavity, and that is given as E naught into cos of m pi x by L into cos of n pi y by W, similar to how you write for TE10. And here L is the length of the patch along the x-axis, and W is the width of the patch along y-axis. Now next parameter is gain. So gain is usually around 7 to 9 dB. Usually in view of the following things, if you consider, that is, gain of the patch from the directivity relative to the vertical axis is usually around 2 dB. If you consider length of the patch is half a wavelength, and if the patch is of square shape, then the pattern will be directional. So that counts for almost 2 to 3 dB gain, and along with that, if you consider the ground plane is cut off or almost all radiation behind the antenna is cut off, then the gain will be increased by 3 dB. So considering all these parameters, the gain will be around 7 to 9 dB. Now next is bandwidth. So usually this bandwidth is strongly influenced by the spacing between patch and the ground plane. So as the patch is moved closer to the ground plane, less energy will be radiated, and it is also a factor of quality factor. Bandwidth is given by S minus 1 divided by Q naught into root of S. Q naught is the quality factor, and root of S is the voltage standing wave ratio. Now quality factor, usually microstrip patch antennas have a very high quality factor. This will represent the losses associated with the antenna. Q will lead to narrow bandwidth, and a low efficiency Q can be reduced by increasing thickness of the dielectric substrate. But as the thickness, if you increase, what happens is a large fraction of the total power delivered will be transformed into a surface wave. Next parameter is efficiency. So the total loss factor is given by the equation. Total loss is equal to LC plus LD plus LR, where LR is the loss in radiation, LC is the loss in conductor, and LD is the loss in the dielectric. So the radiation efficiency will be equal to the total power radiated divided by PC plus PD plus PR. So PR is the radiated power, PC is the power dissipated due to conductor loss, and PD is the power dissipated due to dielectric. So next parameter is polarization. So polarization is how the pattern basically will be. So this can be designed, patch antennas can be designed to have vertical, horizontal, right hand circular or left hand circular polarization by using multiple feed or single point feeds. So depending upon what you want to achieve, if you want circular polarization, you can use a square patch, which is excited by two feeds with the inputs having a 90-degree phase shift. And if the level of two currents in this case will be such that vertical current flow is at maximum and the horizontal current flow will be at minimum. So you obtain circular polarized. And So in this case, you can obtain circular polarized wave. So depending upon which way you want, accordingly you have to design it. Next parameter is return loss. So return loss is defined as ratio of Fourier transform of the incident pulse and the reflected signal. So it's a ratio of incident pulse and the reflected signal So usually bandwidth of patch is very less, and usually if you are designed to operate at 100 megahertz, usually it will be resonant to nearly at 96 megahertz. So this shift is due to fringing fields around the antenna, which makes the patch appear a little longer. And usually when a patch is designed, it is usually we will trim the length by 2 to 4% to achieve resonance at the desired frequency. Another parameter is radar cross section. Usually the GPS guidance systems all require low radar cross section. So if you want to reduce the RCS, it is achieved by what we do is we will cover the patch with a magnetic absorbing material, but this will reduce the gain of the antenna. Now next topic is, so these are the different parameters you should be knowing. Now next is impact of different parameters on characteristics. So first one is width. So width controls the input impedance and the radiation pattern. So the width is usually given by the formula C by 2 into F naught root of epsilon r plus 1 divided by 2. So this epsilon r, which is permittivity of the substrate, this controls the fringing fields. So if this is lower, then the fringing field will be less, wider will be the fringing field and better will be the radiation. And decrease in epsilon r will reduce the bandwidth. And length is given by the formula 1 by 2 fc root of epsilon naught epsilon r into mu naught. So the efficiency can also be increased with the lower value of permittivity. So effective permittivity is increased by a factor of 4. The required length will decrease by a factor of 2 because this is in root. Also another parameter is height. So increase in height will increase the volume. So the bandwidth is also bound to increase. So this height will control the bandwidth. And height is increased will induce a surface waves that travel within the substrate. Another parameter which affects is the bandwidth. So bandwidth is related by, it's proportional to epsilon r minus 1 by epsilon r square into w by l into h. And also we can write it using the proportionality relation as it is proportional to h divided by epsilon r.